Hi, I'm dnix. I'm one of the writers of Machinery Safety 101 and a partner in Compliance Insight Consulting. In this short video, I'm going to answer the question, can a Safety PLC be used for hazardous energy control, and if so, under what conditions? To do this, I want to start out by briefly reminding you about the differences between hazardous energy control procedures, lockout, and blocking of hazardous motion. It's important to understand that I'm going to be basing this discussion on the regulations in Ontario, Canada, and on CSA Z460 as well as ISO 13849. I've provided links to the source for each of these in the notes below the video. The regulations and standards applicable in your jurisdiction may be different. There are two main ways that workers can be protected when the safeguarding systems on a machine need to be bypassed or defeated. The first one is lockout, and the second is hazardous energy control procedures. Both of these methods are part of a hazardous energy control program. Sometimes using lockout is not practicable because of its impact on operations and various other functions. In those situations, other controls can be implemented as long as an effective risk control can be achieved. So let's start with hazardous energy control procedures. Hazardous Energy Control Procedures, or HECPs. Hazardous energy control procedures are administrative controls used when a task needs to be done with the machine's safety systems partially or completely bypassed or disabled, and the machine has to remain energized. When a machine's safety systems are fully operational, the likelihood of injury is usually quite low. But when safeguarding is bypassed for troubleshooting, testing, setup, or some other reason, like convenience, the likelihood of an injury can soar. Hazardous energy control procedures are used to maintain worker safety by preventing unintended release of stored energy in unintended startup, unintended motion, and contact with a hazard when the guards are removed or safety devices have been bypassed or removed. So, lockout, on the other hand, is generally considered to be the most reliable way to protect an individual from hazardous energy because you're bringing the system to a zero energy state. When a system is in a zero energy state, the hazard's been eliminated and because no hazardous energy exists. The hazardous energy control procedure includes a full set of steps to determine the hazards and the risks of each task being performed, and determining what controls can be used to minimize and reduce risk and achieve effective risk control. If effective risk control can't be achieved for some reason, then lockout will be the default method of control. Okay, so let's look at how this lines up with Ontario's regulation. Ontario Reg 851, also known as industrial establishments, has three sections that deal with hazardous energy control. Sections 42, 75, and 76. Section 42 deals with electrical safety when live work must be done. It's a fairly involved section, and I'm not going to dig into that section in a lot of detail in this video just because of time and because I really want to get to the question about using safety PLCs for hazardous energy control. So let's start out by looking at section 75 and 76. Section 75 and 76 fall into the portion of the regulation entitled Maintenance and Repairs. Section 75 reads, "A part of a machine, transmission machinery, device, or thing shall be cleaned, oiled, adjusted, repaired, or have maintenance work performed on it only when A, the motion that may endanger a worker has stopped, and B, any part that has been stopped and that may subsequently move and endanger a worker has been blocked to prevent its movement." So let's break this down a bit. The first piece, a part of a machine, transmission machinery, device, or thing. So basically anything you're using in a workplace where there are parts that might move and which might hurt someone, are covered by this part of the section. Keep in mind, we're talking about power-operated machinery. Devices are things here, not manually operated hand trucks or rolling ladders or anything like that. The inclusion of device or thing is really lawyer speak and is in there to make sure that no one can argue that their power-operated widget isn't included by the regulation. Basically, if you've got a piece of equipment that's being used in a workplace and it has a power source that's part of what makes it move, it's covered. Okay, so moving on. Let's look at the next part. Shall be cleaned, oiled, adjusted, repaired, or have maintenance work performed on it. Okay, so you want to be able to do one of these tasks. Here's where things get to be a bit more difficult. There's no detail given about what those tasks might include, and there is nothing in the regulation that speaks to time. So we'll come back to this in a minute, and I need you to hold that thought, particularly keep the idea about time in your mind. All right, so the first bullet reads, A, motion that may endanger a worker has stopped. This makes sense if you're trying to keep people from getting hurt. The machinery should not be moving, so we need to have it stopped. Bullet B reads, any part that's been stopped and that may subsequently move and endanger a worker has been blocked to prevent its movement. Motion must be blocked. This is the key word here. There is no definition in the regulation for what blocked means in this context, so we need to go to the dictionary to see what it says. So the definition for blocked says that it's to make movement or flow in a passage, pipe, road, etc. difficult or impossible. And some of the examples that are given are things like blocking up holes with sticky tape, or narrow roads blocked by cars, or maybe a blocked nose. Ultimately, what we're talking about here is putting some kind of an obstacle in the way of something else. That's really what that term blocked means. Since it's not defined in the regulation, we have no choice but to use the dictionary definition, so we're going to go with that. Okay, so we know we need to put something in the way of hazardous motions while the machinery is cleaned, oiled, adjusted, repaired, or having maintenance work performed on it. So let's look at section 76, and then we'll look at the differences between these sections and see how that all works. Section 76 says, where the starting of a machine, transmission machinery, device, or thing may endanger the safety of a worker, A, control switches or other control mechanisms shall be locked out, and other effective precautions necessary to prevent any starting shall be taken. All right, so we're going to break this down again. So the first part, where the starting of a machine, transmission machinery, device, or thing may endanger the safety of a worker. Well, those keywords that we need to keep in mind are starting and endanger the safety of a worker. So if the machine can start up, we may need lockout. And if there's a potential that we're going to endanger the safety of a worker, we may need lockout. The machine can start, but there's no hazard associated with it starting, which is probably pretty unlikely, but let's cover it, then there's probably not a reason to go to lockout. So it's that endangering a person and the startup of the machine, and this is really talking about unexpected startup of the machine. These are the circumstances where lockout is required. Okay, so if that's the case, then we need to follow A, control switches or other control mechanisms shall be locked out, or B, other effective precautions necessary to prevent any starting shall be taken. So here's where we start to have some difficulty, because the text of the regulation and the way it's applied in practice sometimes differs. Bullet A talks about control switches. Now, generally, unless the control switch is an electrical disconnect, placing a lock on, for example, an emergency stop device, is not considered to be adequate. And here's where section 42 begins to be important. So let's look at the first two subsections in section 42. So 42.1 reads, the power supply to electrical installations, equipment, or conductors shall be disconnected, locked out of service, and tagged before any work is done. And while it is being done on or near live exposed parts or of the installation's equipment or conductors. Section 42.2 reads, before beginning the work, each worker shall determine if the requirements of subsection 1 have been complied with. Okay, so every worker is responsible for ensuring that lockout's been done correctly. And so they need to be able to go back and verify that the electrical equipment has been disconnected, locked out, and tagged before they do any work, and for the entire duration of time while it's being while that work is being done. Earlier I mentioned that Section 42 covers the requirements for electrical work, and as you can see, there is a requirement that electrical equipment is disconnected, locked out of service, and tagged before and during the work on the electrical equipment. But this really ultimately is where the requirement for disconnection comes from, and CSA Z460 backs this requirement up in a few places, starting out with the definition for lockout. So let's look at that. So 460 defines lockout as the placement of a lockout device on an energy isolating device in accordance with an established procedure. So you need a lockout device, you need an energy isolating device, and you need an established procedure, right? So to really understand what this is about, then we also need to look at the definition for an energy isolating device. So an energy isolation device is defined as a mechanical device that physically prevents the transmission or release of energy, including but not limited to the following: manually operated circuit breaker, a disconnect switch, a manually operated switch by which the conductors of a circuit can be disconnected from all ungrounded supply conductors, a line valve, a block, and other devices used to block or isolate energy. And there's a note that comes along with this definition that says push button selector switches and other control type devices are not energy isolating devices. Okay, so little jog off into the weeds here. Where you see something that's prefaced with the word note in a standard like this, whether it's in a definition or later in the body of the standard, wherever you see that word note, what it's telling you is that everything else that comes after that is what's called informative text, which basically means it's just there to help you understand whatever the preceding text was that you just read. Okay, so the definition that we just read for an energy isolating device is normative text. That means it contains requirements that are part of applying the standard. Now, if you're not using Z460, maybe you're watching this video from the US and you're using ANSI Z244.1, or you're using some other standard, the language that we're talking about here may not be exactly the same in those standards, but the approach to using notes to provide guidance information and additional helpful information is consistent regardless of what standards you're reading. So, since the statement about push button selector switches and other control switches not being energy isolating devices is in a note, that means it's not a requirement of the standard, but it does give us a hint here that we can't, for instance, push an emergency stop button, put a lock on that, and consider that to be lockout. Okay, that's a push button switch, can't be used. Okay, cannot be used. It can be used as part of a bigger hazardous energy control procedure. It might be part of the steps in executing your lockout procedure, because lockout is part of hazardous energy control. It is technically a hazardous energy control procedure. So for instance, you could power the machine down, press the emergency stop button, maybe close the locking cover on it, put a lock on it, then go to the main disconnect switch, turn the power off, and then come back and try and restart the machine. That's normally part of the validation in an HECP. And doing it that way is fine because the energy isolation is actually provided by the disconnect switch and not by the e-stop. So the e-stop is simply part of gracefully shutting down the machine and ensuring that you don't get an unexpected restart. Okay, I'm getting off in the weeds here. Let's carry on. So the note really provides you with a key clue, and that basically means that normal control devices and the control circuits that are associated with them can't be used for energy isolation. And the other part is that since lockout requires the placement of a lockout device like a padlock on the energy isolating devices, generally control type devices can't be used. They don't isolate energy, and for the most part, they don't accept locks. All right, so how does all of this fit together? If we're doing maintenance tasks like the ones that are described in Section 75, we need to block hazardous motions, but it doesn't necessarily require lockout for all of those reasons. It might, okay? It might require lockout, but not necessarily. But if there's any kind of a possibility that the machine could unexpectedly restart during the time that the motion is supposed to be blocked, then blocking is probably not enough, and you will need to go ahead and implement a full lockout. Now, the other problem we have is that the word maintenance isn't actually defined in the regulation, and for that matter, it's also not defined in Z460. So we have to go back to our dictionary for that and see what it happens to say. So let's look at the definition of maintenance. So maintenance is basically the process of preserving a condition or a situation or the state of something being preserved, or it's the process of keeping something in good condition. And I think in industry, probably that second bullet is the most correct for what it is we're talking about. So keeping this in mind and keeping the definition of blocking in mind, remember we're trying to put an obstacle in the way of something, then we need to carry those ideas forward as we read Z460 and the regulation. Now, interestingly, Z460 does include the word blocking as part of a lockout procedure. So it's one element that can be used as part of preventing unexpected startup. So if you're going to follow the regulations, anytime a worker's safety might be endangered by the starting of a machine or by hazardous movements, then the movements need to be blocked and the energy sources must be locked out. And, you know, bear in mind here, I've been sort of focusing on the electrical disconnect and so on, but we're talking about any source of energy. So this could be gravity, steam, water, you know, anything like that. Counterweights, that's gravity, but basically any source of energy that you might have. Could also be chemical energy, or solar energy. Locking out solar panels has actually become kind of a thing. It's a difficult thing to do if the system's not designed well, because obviously you can't go up and switch off the sun. That would be, you know, a little bit difficult to do. So what I've generally found is that there are some circumstances where the ministry may allow you to deviate from this requirement. Section 76B kind of hints at the possibility when it says that other effective precautions necessary to prevent any starting shall be taken. However, you need to remember that this bullet has to be read with bullet A, and it's really speaking to the fact that blocking must be used along with lockout. So we're gonna switch off power, isolate the energy, put a lock on it, and we may also need blocking for gravity and other things. When it comes to minor routine repetitive maintenance tasks that take a short amount of time and minimal tools, then using the machine's interlocks is often enough. That short time frame, I talked about short time frame, usually it's considered to be 15 minutes, maybe up to 30 minutes. Really anything longer than that is too long. And you'll see actually when we start to look at the calculations that I'm going to show you at the end of this video, a little bit about why that's true. So basically anything longer than that is really starting to push the envelope. And if you think you want to try using the control systems to block motion rather than do lockout on a piece of equipment, I really think that I have to recommend you do two things. You need to talk to the regional engineer for the Ministry of Labor and get them to have a chance to look at the proposal that you're putting together and decide if they think that it's going to meet the intent. And you may also want to talk to one of the consultants from WSPS, that's the Workplace Safety and Prevention organization. It used to be called IAPA. They have consultants that you can ask to come in. It doesn't cost you anything to have them come in. It's a subsidized service, and they can also give you their opinion about whether what you're proposing is going to work. I also want to say, don't build any of this until you have put together a proposal for how it is you expect it to work, and you can present that to these folks, because it would be it could be a very expensive mistake to go ahead and build all this stuff and then bring them in and have them look at it, because if they're not going to accept it, you just spent however many hundreds of thousands of dollars making the changes. So the other thing to keep in mind is Regardless of whether the ministry inspector actually decides that this process that you're proposing is going to be something that they think might meet the intent, you need to remember that no matter what happens, as an employer, you bear the full liability for any injuries that occur on your equipment. You can't delegate that responsibility to anybody. So even though you've had the Ministry in the Ministry of Labor engineer come in and review it and tell you he thinks it's okay, and maybe you've had WSPS come in, maybe you've had me come in, maybe you've had your PSR engineer come in and look at these things, and everybody's in agreement, yeah, it looks like it's going to be okay. If somebody gets hurt, as the employer, you carry the responsibility. So you need to be clear about whether or not you're comfortable with carrying that liability. Because anytime you let workers inside a machine with hazardous energy available, you're running the risk of somebody getting hurt or killed. And that's the bottom line. Now, the other thing I wanted to say is the time limits I mentioned are not documented anywhere. So you can't look in Z460 and find the 15 minutes to 30 minutes. You can't look in Reg 851 and find it. You can't look in the Occupational Health and Safety Act and find it. These are general rules which knowledgeable people have generally considered to be okay for this kind of a circumstance. It's just that. It's a generally agreed upon acceptable way to do things, but it's not documented. And I would say that if you want to try to go beyond those timeframes, that you're getting into some difficult territory. Okay. So this whole discussion then brings us around to the key question, which is, can a safety system like a Safety PLC be used for lockout? One of the key aspects of the definition for lockout is that the isolating device is a mechanical device. Okay, so we need to go back and look at that definition again just to keep it in our mind here. So energy isolating devices are a mechanical device that physically prevents the transmission or release of energy. Okay, those are the key words when we're thinking about that energy isolating device. Then they give you a list. Okay, so I want to have a look then at the basic information surrounding disconnecting devices, and I'm actually going to do a reliability calculation with you here, and we'll have a look at how that lines up with our PLCs and so on. So one of the things about disconnecting devices, particularly safety disconnect switches like the ones that I'm calling out here, and by the way, I want to say just for a second, I'm not attacking anybody here. This is not any kind of a commentary on any particular device or manufacturer's product or anything like that. All I did was simply pull some real world data that I could do some calculations with as an example. Okay, so I'm not endorsing these products, nor am I saying that these products are a problem and you shouldn't use them. It's simply data to be used. Okay. So with a disconnecting device, a safety disconnect switch, you can pull the handle on the device, and then you can either open the door or look through a window in the case and see that the contacts are open. All right, so you have an easily verifiable state that you can check. And they're designed to take a padlock, so you can put a padlock on them. Now you know that that state isn't going to change. And you could do the same thing with a valve. Valves that are intended for this purpose usually have an indicator on them so that you can tell when they're closed. You can back up either of these devices with a meter or a voltage indicator or a pressure gauge or something that will allow you to validate or verify that the pressure downstream has been released, or that that there's no voltage present on the equipment. Okay. So I've heard some knowledgeable people, and by the way, this is a discussion that has been going on in the safety community, and particularly with functional safety specialists. We've been talking about the use of safety PLCs and interlocks and so on as part of a hazardous energy control procedure for a long time. Like probably more than 15 years that I can think of. And I've heard some really knowledgeable people say that, you know, safety PLCs have direct control over the power contactors, they've got diagnostics, they've got all that good stuff built in, and so they're absolutely as safe as using an industrial disconnect of some kind. So to really put some meat on those bones, I wanted to look at the reliability requirements. Okay, so when we look at the upper set of data, that's from an AB1494G switch, and you can see Allen Bradley's given us both mechanical operational data and electrical life. And so for the electrical life of the switch, they're talking 6,000 operations at rated current. So assume that the machine was running. You probably wouldn't normally do this, but if the machine's running, motor's running, and you pull that switch while it's running, you should get 6,000 operations out of that switch if the motor or the machine is pulling the full rated current of the switch. If we look at the Square D H367, you'll notice that the lowest number on the chart under UL98 is 8,000 operations. For the more lightly loaded switches like the 30 and 60 amp switches, they're talking 10,000 mechanical operations or electrical operations. Square D doesn't actually give us quite the quality of reliability data that Allen Bradley does, but anyway, this is what we have to work with. Okay. So when you look at those two switches and their data, what you'll see is that their lifetimes are fairly similar. 6,000 operations, 8,000 operations. Okay. So what I did in order to be able to make a reasonable comparison of the worst case, I took the worst case numbers from these tables and I did the calculations using that. Okay. So I had to go on and make some other assumptions as part of doing the calculations. So let's look at what I did here. Now, these calculations come out of Annex C in ISO 13849. So I had to make some assumptions. The mission time is 20 years, so the A on this slide means years. Okay. The mission time is not explicitly stated in ISO 13849, but it is the implied lifetime of a machine. And basically what we're talking about is the time between the times that you have to gut and replace the electrical control system. Okay, and typically 20 years is about right. Then we have the proof test interval, which is also 20 years. Proof testing is the process of testing the control system to make sure that, first of all of the detectable dangerous failures are detected, and also to ensure that there are no undetectable dangerous failures left after the control system has been put into service. So normally under 13849, the assumption is that's done at the factory when the machine is new, and then the next time it would be done is when you replace the control system, which is 20 years down the road. So that's why the mission time and the proof test interval on this slide are the same. Next thing we need to know is how long or how many operations we can assume from a switch like this between failures. Okay, so unfortunately, neither Allen Bradley nor Square D provide us with what's called B10D, which is the number of operations of the device before 10% of the units in a family or in a selection, in a group of those switches fails to danger. So B10, the 10 is 10%, the D means dangerous, B10D. Okay, so since we don't get that data directly from the manufacturer, we have a bit of a problem. But 13849 tells us that for electromechanical devices, we can essentially double the rated life of the product to give ourselves B10D. So if we look at the Allen Bradley switch, we're looking at 6,000 operations for B10, okay, and 8,000 operations for B10 on the Square D. Now, if you've ever looked at the reliability bathtub curve, what we're talking about here, that B10 point, is where the curve comes off the horizontal and just starts to climb. That's that curve as you come off the horizontal and begin to climb. That point is wear out. That's the start of the end of life. And so B10 marks the point at which 10% of the switches that exist are now starting to fail. And that's the beginning of that curve. So for the sake of our calculations, for the Rockwell switch, the AB switch, we can double that. So that takes us from 6,000 to 12,000 operations. We can put those 12,000 operations into our calculation along with a couple of additional assumptions. So the next assumption is the number of operations. And I've got that listed as 1 per W, which means once per week. So I'm assuming that for this situation that we're talking about, we're going to be switching off and locking out the power with this switch once a week. Okay, so we go through and we do the math on this, and I'm showing you my calculations, and we come out with MTTFD, that's the mean time to dangerous failure, of 2,308 years. And that seems like a huge number. That doesn't mean that any individual switch is going to live 2,308 years. What it actually means is that if we had a sample of, let's say, 100 switches that were being tested, we could say that after 2.3 years, we would expect to see 10% of those switches fail dangerously. Okay, so that's what MTTFD is about. The other number that we have to calculate is what they call T10D, and T10D is the length of time before we start to see the 10% of the product failing dangerously, and it's based on MTTFD. So we take the B10D value for the switch, 12,000 years, and we divide it by the number of operations per year. In this case, it's going to be 5.2, and we end out with 230 years. Okay, so that's basically how we get to that number. Now, there's one other number that we need, and that's what they call PFHD. PFHD is the probability of dangerous failure per hour, and that is actually the underlying number that we use for many of the calculations in 13849. So I've converted the MTTFD into PFHD, so we have those numbers to compare when we look at the drive systems. So the PFHD for our first case for the AB switch is 5.14 times 10 to the minus 8th failures per hour. Very, very small number. So that would be the same as 0 plus 8 more zeros, 514. Okay, that's basically how we get to 5.14 times 10 to the minus 8th. And for the square D, 16,000 operations for B10, we do the same calculations, and we end out with 3,077 years for the MTTFD. And I notice on the slide I've actually forgotten the decimal in the calculations, I think. No, that's right, 0.1 times 52. So we take 10% of the operations. So when we calculate the MTTFD, then we calculate 3.86 times 10 to the minus 8th failures per hour for the PFHD. And our T10D for the switch is 308 years. So why do we care about T10D? Well, when we're looking at the mission lifetime of a piece of equipment, and we're looking at the T10D for each piece of equipment, that number is significant only if T10D is less than the mission life. So for instance, if we did the calculation on the Rockwell switch and we discovered that its T10D was, let's say, 15.3 years, what that would tell us is that on our PM schedule, we need to have replaced the main disconnect at 15 years. And we would have to do that if we wanted to keep the operational reliability of the system. So when we come to shutdown in the summer, thing one that we would do in year 15 would be to rip the disconnect out and put a new one in. Okay, so that's where T10D comes in. It doesn't have any more significance. than that. And we certainly wouldn't wait 230 years to replace the switch. Again, what that means is if we had 100 switches and they were all operating at the same time under the same conditions, that we would expect that somewhere around 0.2 years we would need to start replacing those switches in order to maintain the reliability, so to prevent failures. Okay, so let's go to the PLC and drive combo. So this time I only picked on Rockwell because it was easier to get the data from the ABE products. So the safety PLC I selected was the SmartGuard 600, and I went into the manual and pulled out their information, and unfortunately they don't give us B10D or even PFHD. They only give us the performance level. So they say that the SmartGuard 600 is PLE and category 4. So that's basically the data that we have available to deal with for the safety PLC. And then for the drive I picked, it was a PowerFlex 700S. They don't give us anything other than performance and category either. So they say that the PowerFlex 700 is PLD category 3. So we can make some educated guesses about what that actually means. And by the way, when a manufacturer gives you performance levels and categories like this, that means that you can treat their product like it's a black box. You don't have to do any deep dive analysis inside their product because they're already telling you what the reliability level is. Okay, so if we look at the safety PLC, then I calculated, or I went actually to Annex K in the standard and looked up the range of PFHD represented by performance level E category 4. And that runs from 9.54 times 10 to the minus 8th failures per hour to 9.06 times 10 to the minus 10th failures per hour. So that's the band that we're dealing with. Okay. And for the drive, PLD category 3, look it up in Annex K, and that runs from 9.21 times 10 to the minus 7th to 1.03 times 10 to the minus 7th failures per hour. Okay, so I took the worst case information for both of those devices, and actually, it looks like in the calculation I took the worst case for the safety PLC and the best case for the drive. Okay, oops, my bad. Anyway, did the calculation. One of the things that you can do with PFHDs, and you can also do this actually with MTTFD, is that if you have a series of black box units connected together in your safety system, you can actually simply sum the failure rates in order to get the overall failure rate of the system. So I summed the PFHDs here, and when we add together 9.54 times 10 to the minus 8th and 9.21 times 10 to the minus 7th, we get 1.02 times 10 to the minus 6 failures per hour. Wow, okay, so why do we care about this? These are tiny numbers, tiny numbers. So we need to do a little bit of a comparison here. So if we look at the disconnects, I've got the disconnects listed up there on the left-hand side of the slide, and you can see the numbers that I calculated there, 5.14 and 3.86, okay? And then on the safety PLC slide, 1.02 times 10 to the minus 6, okay? And I didn't include in that safety PLC drive combination an interlock switch. I could have, but that would have made the situation even worse because in fact, at that point, I'm adding in the additional failures that the interlocking device might have, okay? And so that 1.02 times 10 to the minus 6 would definitely get even bigger. You know, we might be into 10 to the minus 5th or 10 to the minus 4th numbers by the time we add in that interlocking device. We're already in a situation where the safety PLC options failure rate is an order of magnitude greater than the disconnecting device. An order of magnitude is 1,000 times, okay? And so we're an order of magnitude worse with the safety PLC and the drive with STO than we are with just a plain Jane safety disconnect switch, okay? So these numbers are tiny. They're really tiny. And so the difference between the two, while it's significant, shouldn't scare you too much. But let's look at this a little bit more deeply. So when we look at Annex K again, I find that 1.02 times 10 to the minus 6th failures per hour is in the same range as performance level C category 2 with DC average of low. Okay, and if I read across to the edge of the chart, what I find is that PFHD number and those that category in DC equates to an MTTFD of about 56 years. Well, that 56 years is starting to get close to our mission life, right? It's still 3 times what our mission lifetime is, so that means that in our 20-year lifetime of the equipment, we're not in a situation where we're going to need to replace this safety PLC and drive, because the MTTFD for that system is longer than the 20 years. Now, if I added in the interlocking device, then we might be in a situation where we are now less than 20 years. I don't know. We'd have to do the math, okay? But the important thing to remember here is those numbers are very, very small per hour. We're still in the 0 plus 6 digit or 6 zeros before we get to the failure rate. So we're not in a situation where the safety PLC is going to imminently fail. That's not what we're talking about here. But when you compare the two, you can see that a plain electromechanical interlock is significantly more reliable than the safety PLC plus drive. So if you're picking a system to try to protect the safety of workers, using the disconnecting device is more robust a solution, and it's also less expensive than trying to do the same basic thing using the safety PLC and claiming that it's equivalent, because they're not equivalent. All right. Okay. So I think really we've answered the question using reliability. And since power remains available, if you're trying to use the PLC drive combination, then you're in a situation where if something goes wrong, and it is quite possible, especially in when we're talking about systems that are using category 3 architectures, it's quite possible to have undetected dangerous failures that can occur that the diagnostics in the system can't diagnose, can't detect, and it's still possible to lose the safety function. Okay, category 3 and category 4 both require that they are single fault tolerant. So what that means is the system will continue to operate normally with a single fault, but you're relying on the diagnostics to determine whether there are any other faults. And so in in category 3, because the diagnostic capability is only 60%, and in performance level E, we're talking 99%, there's still a significant population of undetected dangerous faults that may exist that you can't tell if they're there. The only way to check for them is proof testing, and the thing is you don't want to proof test too often, because you can also affect the lifetime of the equipment if you're doing proof testing too often. Okay, so based on 20 years mission time, 20 years proof test interval, that's what we're talking about. So because the power is still on with the drive and safety PLC, the concern that I would have is that it's entirely possible if one of those undetected dangerous faults occurs and you already have a single fault existing in your system, that you may be in a situation where you lose a safety function and you don't know. All right. So my money would be on the disconnecting means, personally, for dangerous situations. But that kind of brings us back to the first step, and the first step is always do a risk assessment. And so if you're trying to determine, are we going to use lockout, or are we going to use hazardous energy control, or are we going to use some combination of those two things, thing one in this process is a detailed risk assessment, because if you don't do that, you don't know what's happening, you can't make rational decisions, you will screw it up, I guarantee you. If you don't do a detailed risk assessment, it's got to be done. Okay. The other thing that's interesting here is that CSA Z460 doesn't talk about this topic of deciding between electromechanical devices and electronic control systems at all. The definition for a lockout in Z460 is that you're using a mechanical isolating device to isolate power from the machine. So there's no discussion in 460 about, oh, maybe we can use a safety PLC for that purpose. It's just not done. Okay. So I think really in wrapping up, I need to say that, you know, for short time, simple maintenance tasks, minimal tools, minimal skills, minimal disassembly of the equipment, you can probably do those just using a guard interlock. You know, somebody needs to replace a busted drill bit or go in and squirt a little bit of oil on something, sure, you know, that's probably fine. But if you're going to do anything that's going to take more than a few minutes, or where you're disassembling the machine, then you need to go to your full lockout procedure. Okay. You know, the consequences of a failure here can easily be a fatality, or if you're lucky, a severe injury. Okay. And so I think that particularly for any kind of work that's going to take more than a few minutes, it only makes sense to take the time to properly lock a piece of equipment out before you do the work, because it's somebody's life that's on the line here. You know, if you're unsure, I would really encourage you to contact a knowledgeable person. Talk to the Ministry of Labor's regional engineer. Talk to the WSPS, talk to somebody like me, talk to your pre-start engineer, and make sure that you're developing a system that makes sense, you know, and whatever you do, don't guess. Okay, well, so that's it for this particular Q&A. If you have any additional questions or comments, you can leave them on our YouTube channel in the comments, or there'll also be a link if you look below the video here on the blog. You'll find a way. There's a comment box down there. You can leave comments there, or you can email me. I'll make sure my email link is in the notes, and I'd be glad to talk to you about your concerns. Okay. Have a safe day, and we'll talk soon.